Good morning, everyone. Welcome to the Cafe webinar series co-hosted by Department of Bioengineering at UCR. I'm Jin Nam, Associate Professor of Bioengineering, and it is my great pleasure to introduce our webinar speaker today, Dr. Kiruba Krishnaswamy. Dr. Krishnaswamy is an Assistant Professor in the Department of Biomedical, Biological, and Chemical Engineering with a joint appointment in Food Science at the University of Missouri. She received her PhD degree from McGill University with a focus on bioresource engineering. And for that, she received the Best PhD Thesis Award from the Canadian Society for Bioengineers. She is currently working on food engineering and sustainable technologies to address the challenges of food and nutrition security. Today, she will present a talk titled Imagine a Zero Hunger World is Within Reach. Let's welcome Dr. Krishnaswamy.
Thank you, Dr. Jinnan, and thanks everyone for joining me for today's session, and also to the organizers for inviting me for this talk. So let me share my screen. So as the talk says, imagine a zero hunger world, and it's within reach. So let me say my aspiration or my vision, how we could have a zero hunger world. So currently, like when we started in 1950, we were around 2.5 billion people on this planet. And now in 2020, we are around 7.5 billion people on this planet. By 2050, it says like around 9 to 10 billion people are going to be on this planet Earth. But within the boundary conditions, the big question that we all have is, how do we feed this 9 billion people sustainably with healthy food? That's a grand challenge, right? And so that's why we need transdisciplinary teams together to address this grand challenge. And what happened is, why I was interested in food systems engineering is because when we started this 21st century, we did see a lot of calamities. We saw from floods to fires to droughts to most of the natural calamities that affected us. And currently we are in a global pandemic, right? And what has this pandemic exposed is, it has exposed that vulnerable people are affected drastically from any natural disaster or to a pandemic. Around 80% of people living in rural areas, in coastal areas or tribal groups are affected by hunger. And also 20% of people living in urban areas, food deserts, are also affected by hunger. And COVID also exposed something much more deep, that it exposed the social disparities in the world, throughout the world. And that is something that, that was brought to limelight. And currently, whenever we talk about hunger, we always think about chronic hunger. So chronic hunger is like, around 821 million people on this planet are affected by chronic hunger. That is 1 in 9 person is affected by chronic hunger. But I'm here to talk about something much more dangerous, and that is called, like, 21st century, we shouldn't be talking about chronic hunger, first of all, but unfortunately we are. And imagine what is going to be the state by the year 2050. So those are questions that, like, to the students in the group or to researchers that we want to think about how we're going to address it. And as I said, I'm going to talk about something much more dangerous, which is the hidden hunger. This affects more than 2 billion people on this planet, irrespective of a developing country or a developed country. And this is due to micronutrient deficiencies. And also, we leave around 7 million children before they reach their 5th birthday annually because of malnutrition problems. So we see children are our future, but we leave around 7 million children annually. So that is something that, is a big challenge that needs to be addressed. And so what is the vision of my research program is connecting all these dots. On one hand, we have around 2 billion people affected by hidden hunger. And whenever we talk about hidden hunger, we always think about wasting and stunting. Yes, that is one part of the spectrum, but the other portion is also overweight and obesity. And this is what we call the double burden of malnutrition. And recent studies have been shown that micronutrition deficiencies play a critical role in both these malnutrition areas. So one hand we have this, but on the other hand, around 1.3 billion tons of edible food is wasted annually. So what if we learn the power of transformation from nature? Because in nature, there is nothing called waste. Waste is a terminology that was created by humans, right? So if we could learn the power of transformation from nature, then we will not be calling this as waste, but rather raw materials for a process. And so that's what we need to zero waste processing to recover micronutrients to address this problem. So this is kind of a vision for my research program. And I do know it's a complex challenge. There is no single bullet to solve this, but everyone can contribute. So how we are contributing from our research program is through these three areas. One is sustainable food systems engineering, where we do a lot of upcycling of food-based food loss, predominantly focusing on underutilized native fruits, vegetables, and plants. So once we are able to recover these micronutrients, then we fortify them to develop ready-to-eat therapeutic food addressing hidden hunger. And then whenever we are fortifying foods, since they are all vitamins and minerals, you need to have a barrier, a delivery mechanism. That's why we come up with innovative technologies for effectively delivering these micronutrients through encapsulation. So all these three things, you see, it's connected with zero hunger. So we try to align most of our research with the SDG 2, that is zero hunger. And our lab is called the Feast Lab. And the interested population groups are women and children in urban, rural, and tribal communities. So that's a small portion that we want to contribute to this big grand challenge. So here, what I'm going to do is, as I said, it aligns with the zero hunger. So I have two examples of research that I want to share with you today. And I'm just going to give a brief overview of these two research. If you want, we can discuss about it in the Q&A session. So the first one that I want to discuss with you is upcycling of food waste and food loss. One is a value addition to indigenous crops to recover micronutrients. So this particular crop that I'm going to talk about is millets. The next year, the year 2023, is declared as the International Year of Millets. So we'll be learning and reading about millets a lot the next year as well. The UN has declared it. So why these are important? These are underutilized ancient grains. They are drought tolerant, they're climate resilient, they have health promoting compounds, and they could be considered as functional foods. Currently in the US, they are used as animal or bird feed, but apparently they are gluten-free and they are high in proteins, fibers, vitamins, and minerals. So that makes this ancient grain. And it used to be grown in this area. And researchers like Dr. Rob Myers at the University of Missouri have proven that the Midwest is the conditions for growth for most of these millets are quite good. So that's why we've taken this particular ancient grain to study its properties. So what happened in the year from 1950 to to the 2000s, if we see the global yield of millets, initially they were quite high, but then there is a drastic, let's take for Asia. After the 70s, you could see a steady decline in the yield or the production of millets. And recently there is an interest in ancient grains. That's why we could see a trend, a positive, moving a little bit upwards. So why, that leads to the global trend as well. And so why millets is because they are grown throughout the Asia as well as in Africa, that belt as well as different parts of the world. You could see this is a list of millets, and the major producers are Latin America for amaranth, Latin America, US, India, Africa, China, Eastern Europe, and Russia. So, and in different parts of the world, they're called with different names. So that makes it people have been using these ancient grains throughout the world with different names. And now we tried in this paper to consolidate different names and different millets, from banyan to finger to kudo millet to pearl, little millet, and to see how they are distributed throughout the world. So that was a very interesting overview. And when we were studying this in this paper, what we found is there were less information about the physical and the functional properties of these millets. So these images that we see are the first electron microscopic images of these small millets. From visual observation, you can see they all look the same. They all look pretty much the same for visual observation. But when we put them under the microscope, that's when we start seeing beautiful structures that that also can be correlated with the functional properties. For example, the amaranth has a beautiful coat that gives it a unique property. And here, the little millet, and you can see the banyan millet, you can see there is a the surface degradation. This is because they are shelled. Most of these millets are shelled, and during that shelling process, or the hulling process, there is a mechanical damage. That's why we can see such structures for kudo, for banyan, and for little millet. But in the case of pearl millet or a sorghum or a porso millet, we don't see such thing. That's why you have a very smooth surface. And why this all is important is because if we are going to study the physical properties like angle of repose or bulk density, porosity, these small changes in the structure could have an impact. And also here, this is for the finger millet. So you can see, if we go for a higher magnification for the finger millet, we can see small micro fibers, and that's why it's easy for it to the structure is beautiful in such a way. The angle of repose also is the properties are interesting for the finger millet. So once we put them under the microscope, then that was quite interesting for us to study these millets. And also, regarding the functional properties, we were able to find that these millets, when compared with maize, rice, and wheat, the essential amino acids present in these millets are quite unique. They have a different profile of essential amino acids compared to the major staples that we are currently using. So incorporating them even in small quantities will help us to get most of the essential amino acids, and also the profile of vitamins and minerals available in these millets were quite high. So that led to another paper saying how we can use these ancient grains as a potential towards potential food ingredients or sustainable food ingredients for food processing. So that's a brief overview of how we can take something that is underutilized and wasted to make into products that could be beneficial to improve the health of people. And also by doing this, we can align them with the SDG 2, SDG 12, and SDG 13 because of the connections. We are using underutilized crops that are drought resilient, climate resilient, and also they need less water. So that's how we are connecting the dots with SDGs. So that's one example of using waste materials. The next example that I would like to share with you is about the second quadrant. So first we talked about the fortification, the sustainable food processing. Now we're going to talk about the food fortification, the second quadrant of it. And for this, I've taken this example of double fortified salt. So the double fortified salt is fortified with iron and iodine, which is an interesting, it was a technical challenge, but the outcome of this project is something that I learned a lot from this project. So that's why I want to share with you. It's how we could use sustainable food engineering innovations to address food and nutrition security challenge. So why is because this happens even today. This is a picture of a 2-month-old child affected, lying in a malnutrition intensive care in 2015. It's not too long, right? And currently the COVID has accelerated. This is like such situation we can see throughout the world. And it affects a lot of children under the age of 5. And I'm just talking, so in parts of Africa, India, and different parts of the world, there are pockets like this that it's hard to reach. And how can we reach such vulnerable groups? So that's why this case study is from India. And why India is because it's one of the countries that's worst affected by anemia. Around 56% of women of reproductive age are anemic. So if you see 2 Indian women, most probably 1% could be anemic. So that's the status. And around 70% of children are anemic, and that's the highest percentage record in the world. So because of this, around 6% of GDP is lost every year for this for India, the country. So what it did is this double fortified salt. This is a simplified process flow diagram for the DFS. So we all know our salt is iodized, right? We are consuming the salt that is already fortified with iodine. So how do we make this fortified salt? So you have to see this particular quadrant. How currently the salt that we all consume today is fortified is because we take an iodine solution. It could be potassium iodide or potassium iodate, and it's added to salt with a ribbon blender. It's mixed and it's iodized. That's a simple process for making iodized salt that we all consume every day, right? So, but we wanted to add iron to it. The reason why we wanted to add iron is because salt is an excellent carrier. So if you can see here, the same process flow diagram I've just given in images. So let's see this process flow diagram, and I'll talk to you why we selected salt as a carrier matrix. So if you want to add iron to it, iron and iodine chemically they're not compatible. So the ferrous will become ferric, as well as the iodine can be sublimed, and we'll be losing the iodine that's added to the salt. So that's where we had to come up with a technique so we could have a physical barrier to prevent this interaction. So what we did is we took ferrous fumarate, we agglomerated it, and we cut them into 350 microns, very small size to match the size of a salt. Then after drying, then we did a color masking and also an microencapsulation step. So we could form a physical barrier between the iron and the iodine. And then that forms an iron premix. So when we blend them in a ratio 1:200, then we could easily get a double fortified salt. So that's a simplified overview of this whole process. And if you could see here, this is how ferrous fumarate looks like. And once it's agglomerated, like this is how it looks like. And after it's coated with titanium dioxide, it looks like this. And when we mix it with salt, you can see, like, it matches the size of the salt. So you could ask why salt, right? And this is an image after for the encapsulation step. You can see these are all the pores without encapsulation, and this is after coating. So, someone can ask why salt. The reason why salt is consumed by everyone, irrespective of their age, their social status. You cannot eat too much of salt. We can only have a specific quantity of salt per day, and gender neutral. It doesn't, like, in a country, whenever we are selecting a vehicle like this for a development project, we have to see who is our group and can we reach that. Can the product reach them effectively? So irrespective of their social status, the caste, the gender, salt is consumed throughout. And that's why we selected a vehicle like salt. And so after storing them at different temperatures and humidity levels, this particular formulation, we developed a series of formulation, of which this particular formulation performed really well. So in the lab scale, it worked well. Now we had to pilot scale it. So we, to say this whole story, how this was pilot scale up. So what happened is, The whole story, why I'm saying this, is to show the power of partnership. Okay, the technology was developed at the University of Toronto, where university, researchers, like a team of researchers came together to fix this technical problem. And then the technology was transferred to food industry in India, Jaipur, and along with the salt producers. So we had food industries involved. And then funding wise, we had like the Gates Foundation, the GAIN, international NGOs who were supporting this project. And then like local NGOs like Tata Trust, they were also supporting, because to mobilize the local stakeholders. So we needed a partner on ground. And the government of Uttar Pradesh, government of India, government of Canada. So when we had all these stakeholders together, that we targeted one particular state, Uttar Pradesh, and these were some of the districts where we first pilot tested this particular product. And we were planning to reach 24 million people. So you can see, like from researchers to marketing to stakeholders in public health, public policy, nutrition, and to the end person, like Asha, like the health worker, the frontline worker who goes to home to talk about this product, the infrastructure, everyone had to come together to solve this problem. So first, after seeing the success of this particular project in one particular state, now currently it's reaching 3 states and it's reaching around 16 million people in India. So one small technological innovation could reach so much people. The reason why is because we all eat, right? So if we are all blessed, at least we eat 3 meals a day. And what else will be a wonderful platform if we can give the food with nutritious, with the required nutrition. So that was the power of food that we learned, and also the power of partnership. Because all these teams, when we came together, the only mission that we had is how could we address iron deficiency anemia to improve the health of women and children in vulnerable places. That was the whole question the whole group was asking. Okay, so once one particular state had an impact, then other states wanted it. And now we're trying to pilot scale in Africa. Different countries are looking forward to this technology. So something as simple can have a big impact. And I'm so happy to be a part of this wonderful team and learn from so many amazing individuals. So that's one story I wanted to share about transdisciplinary teams. And as I said, so this particular project, we're able to touch on SDG 2, SDG 3, SDG 5, gender equality, and also the power of partnership. So those were the things that we're able to touch in this project. And so, since we're talking about SDGs, these are some of the SDGs that most of us would have already seen this. But why I want to share this again is because when we saw the MDGs that happened, the Millennium Development Goal to the Sustainable Development Goal that was released in 2015, one key thing is this particular thing, the partnership for the goals. The MDGs had 8 goals, but SDGs are 17. But about everything, this particular goal is something more critical, because we will not be able to achieve zero poverty or hunger or good health, quality education without partnership. And so and I'm so glad the organizers are doing this, like trying to bring people from multiple disciplines and having a platform for us to share this experience. So thank you for you're all doing a wonderful job. Thanks for that opportunity. And let me get back to one more thing, because when the SDGs was released, around 193 countries came together, right? They signed the agenda for this, the agenda for 2030. But when they were signing, we didn't think that something like COVID will come and hit this whole world, and we will experience a pandemic, right? So what happens now with the SDGs is, with the pandemic, it has touched every sector. Without, it has, from zero poverty, loss of income, we saw a lot of people having vulnerable sections of the communities and families fall below the poverty line during the COVID situation. We saw there was a disruption in the food supply chain and production that got disrupted in connecting the zero hunger. Health, obviously, health is like the health outcome due to COVID, and so many millions of lives have been lost due to this pandemic. And in terms of quality education, like millions of children have not been to school for a prolonged period. I think so in the history of human race, this particular lockdowns and the disruption the COVID has caused to the education system could have a major impact. So that's important, because not everyone has access to remote learning, right? So that's an important. And also gender equality, we had issues about this. Most of the we saw increased in violence in certain parts of the world. We saw the distribution of labor due to gender equality became an issue. Clean water was an issue. Some portion of the world didn't even have water to drink. Then how can they have water to wash their hands for COVID, to prevent from COVID infections? Reduced inequalities, affordable energy. Not many people had access to proper energy, so they could continue their education or livelihoods because of that. So decent work and economic growth, that was also restricted. Sustainable cities, people who are living in closed in slums face a higher risk of COVID exposure compared large, highly populated, dense areas were super spreaders of COVID. So the sustainable cities were also affected. And also we saw issues about social justice and peace, that was also affected. But there is one silver lining that we saw. There was a reduction in the environmental footprints during those lockdown periods, though it was a very thin, very small impact, but it had a positive impact. That was a nice silver lining. So when we had, this COVID also made us to reflect a lot about how we as a collective human group are thinking about sustainable future. So coming back to the question that I'm asking is a zero hunger world possible post-COVID, right? Thing is, I am an optimist, and I think, yes, it is possible. And that's where we need transdisciplinary teams. And because most of these things, all these SDGs are still in silos. And it's time that we break these silos and have these conversations, because if we don't break these silos or talk about this, then most of this innovation, those breakthroughs come during those intersection of one silo, one group with another group. So having that platform is so critical. And what I'm everyone can contribute. So how we are trying to contribute here is just made a Zero Hunger Challenge course. It's a new online course. And the whole idea of this course is to bring students from transdisciplinary teams and to think, nurture transdisciplinary thinking about feeding the world sustainably by 2050. And also convergence towards food and nutrition security, aligning with the SDGs. And also we discuss about the partnership for goals, connecting SDG 2 with SDG 70, and having a platform for peer mentorship that mimics professional settings, and to also empower students to become global leaders, because students are the future. If we want to make that change, we have to give that platform to the next generation or the youth who can take it forward and create this world a better place. So it's more team-based, and this particular team, and you can see there's a lot of, it's wonderful discussing with young students because they are really passionate. They just need a platform to express their views, and it's been an amazing journey teaching this course, also learning from them. So that's one that gives me hope that yes, it is possible to imagine a zero hunger world, and it'll come a reality. So my key take-home message is like if we want to have a more sustainable world, it's like, we have to act locally and think globally. And partnership is the key to success in the 21st century. So that's what I would say. And this is my team, and this is an amazing group of grad students I have and undergraduate students. If you want to reach out to us, that's our Twitter handle, that's my email, and this is our website. And this is the contact information for our group. And feel free to contact me. I'll be happy to address any questions that you have about this project. And I think so I was a bit ahead of time, but I'll have a lot of time to answer questions. So thank you for your valuable time. And what I would like to leave is we have only one world, and that's our home. So it's high time we start protecting it. Thank you.
Thank you. Very nice talk. So I am going to see the question. Quinn, do you want to read the question? There is one in the Q&A.
Sure, yeah. Fernando Martinez asks, with most, if not all, good fertile land already in use, will these ancient grains be able to grow on poor land and still provide the nutritional benefits, or will we need to replace some current crops to use our limited land?
Okay, that's a very interesting question. These ancient grains, they are adapted in such a way that they could grow in very less fertile soil. So like they have, and if you see the zones where they all grow, the soil that they, like, in parts of India or Africa, the soil is not alluvial or fertile, but they have been, like, naturally selected in such a way that they can adapt to harsh conditions, from drought resistance to climate resilient. And so that's the beauty of these grains. And also, it's not one particular grain, right? It's a series of crops, like from finger millet to kudo millet to barnyard millet. And the way they are arranged, like, so far from, I'm not a plant scientist to talk more from the plant science aspect, but from a processing aspect, what we see is like it is possible to grow them even in soils that are really poor, and the nutritional profile doesn't change much. That's what we've seen from the data that we got from nutritional profiling. But it'll be wonderful to get some insights from a plant breeding plant scientist to discuss about the yield percentage and so on. But from a processing side, we have not seen any difference in the functional properties of the crops.
Great, thank you. And Zachary Iden also asks, how well will people be able to support livestock with these ancient grains? Will other crops need to be grown for the diets of animal communities of animals communities rely on for transport, agriculture, and food? Sorry, did I read that well enough? Was I clear enough? Sorry about that.
Good enough. So, like the crops, like, these are also called the Indian grasses. Like, parts of native tribes, like, some of the tribes that used to live in the Missouri area, like the Osage nations, they all had these particular grains in their ancient, like, in their traditional ceremonies and so on. So how do they use it? The stalk or the grain comes from the head. So once it's taken, the grass is still there. So this grass could be used for animal feed, and the grain could be used for human consumption. So it could be a win-win for both. So that's how they used to have sustainable agriculture or practices from the tribal community, the Native American communities that lived in the Midwest. So, and I see a similar pattern from the tribal communities that were living in India, and like, some of the communities, like, the Maasai community in Kenya, Africa. So you could see all the trends with these tribal communities, how they use the crop for both human feed as well as for animal feed. So I think so it could be a win-win for both.
Thank you. Do we have any other questions from the students?
I don't see anything, but I do have question. I don't know if Queen has question. And
Go ahead, Deborah.
yeah, I had a couple questions, and one is about the iron. How do you make sure that the range, the concentration in the salt of iron, it's within range for a standard diet intake?
Okay, so what we do is iron, you need to have RDA requirement is 18 milligrams per day. So that's the RDA requirement for a pregnant woman, or like, so RDA gives recommendation for different age groups. So when we develop a formulation, we base it for, okay, we are going to target this particular population group. So then we formulate it for that specific. And then always we add a clearance ratio of addition of 10% and so on. So even if there's going to be a loss during storage, or when a person consumes it, like, they will be able to get enough iron during that period. And also we do a shelf life study. Like, we keep them for storage at accelerated storage conditions, like, 25 degrees, 35 degrees, 45 degrees, and also try to create humidity conditions. Suppose it's going to be in Africa, right? Then we have to simulate those conditions. What humidity levels can it withstand? Can our port withstand that particular temperature and humidity conditions? And once we know, we do all these trial testing in the lab. Once we know this formulation works, then we go for pilot scale.
Thank you. I did put another question in the chat. It's a little bit outside, but I think you are an expert on this. How do we prepare and equip the next generation so that they have knowledge and the skill to address the complex issues that they are affecting agriculture and the global food system? Do you think interdisciplinary and experiential learning plays a major role, or focusing on establishing a consensus body of knowledge is more important? What's your thought about it?
Actually, that's a very challenging question, because students, first thing, they have to get exposure. Experiential learning is really good, because when they learn, when they experience something, that knowledge you cannot take them from what if they're reading from a book or going to a field to do that. So that is completely different. So my top answer is experiential learning will be a wonderful platform for students to understand the problem, they come up with solution. Also, that leads to another thing. You asked me two different thoughts, right? Like ideas, the T model, where students should have a basic idea of some, like, if they are an engineer or they are a scientist, or like whatever their background, they should have some basic understanding of their field, but also they should be able to go back and connect the dots with the broader spectrum. So that's where they can understand, okay, this is the problem. I can go deep. If some problem is given to me, I can go deep into that problem and address it. But also I should be able to come back to the surface and discuss that in such a way that a stakeholder or a partner who is in a different discipline, like, I'm an engineer. If I'm not able to communicate that to a nutrition specialist or a health worker who is in the field worker who is going to transfer my technology to the end user, then that's going to be difficult, right? So I think you need to have both. So, and if we are able to prepare students or the next generation to understand the importance of both and apply it to address a problem, that will be wonderful.
Okay, thank you. I agree with you. Wonderful answer. I think there is another question in the Q&A.
Yeah, from Alyssa Anderson, who asks, as you have shown, there are many contributing factors to sustainable food production. Are you looking at changing public policy to improve agriculture?
That is also a wonderful question, because any action, like, you need to have a policy state. So coming back to that particular, for the example of the fortification of salt, right? We developed the technology, we had all our stakeholders in place, but we had to get the public policy in place. So then we were able to use the public distribution system, like the SNAP program in the US. There's something called the ration shop, like public distribution system. So for that particular process to happen, we had to have a policy in place. So then the technology, the product that we developed could enter those system and reach the people. So all these things are tied up. So whenever we're designing something or designing a program, we need to have people from all the stakeholders, and public policy is so important to make sure that whatever innovation happens reaches the people who are in need. So thanks for that question.
I have a question. Just thinking about, all of the disturbances to agriculture brought on by climate change, like drought and heat waves, et cetera, and thinking about zero hunger moving forward, sort of, do you think that the answer for battling like crop loss is more focusing on drought tolerant plants, or, using native plants that are extremely hardy, or will we need to have global trade still in food? Are we going to have to like ship food around to make sure that people have food in areas that are stricken by drought, or is the answer more focusing on plants that we can grow in areas where there is drought? What are your thoughts on that?
Actually, Quinn, that's a really challenging question, because the problem that we are addressing is a complex problem, right? And there is no one solution, like a solution like this, a drought resilient crop could be working well for one country or one geographical location, but we cannot apply the same strategy to another country which has a different geographical condition or geopolitical condition or something like that. So I would say we need to understand what is the geographical nature, what is the social, economic aspects of that particular, and address the challenge for that group. And also, I see this question has multiple approach, because one, yes, that is a strategy that could be applied, but also supply chain, right? We could take care of all the drought tolerant, like we have amazing plant breeders who can come up with great crop varieties. But once it's from harvested, right? When the post-harvest is done, if our supply chain is not in place, then we're going to have losses during transportation, during storage, during processing, so we have to have all the stakeholders in place in order to address this. And so yeah, it is a complex question, and I would say it is case specific. We have to take case by case and see what would work for that particular scenario and situation.
Thank you for that thoughtful answer. That makes a lot of sense. Thank you.
Thanks for that. That was a very, very difficult question, like important question you asked.
We have 3 minutes until our 50 minutes. So I don't know if there is more question, or I don't see any other question.
I can ask one more question if nobody else has. Inni. I was struck by the finger millet, by just how high in vitamins. Like, it seems like a superfood. So is that true wherever you grow? Do the growth conditions matter for finger millet, and what makes it so special apart from the other millets?
So the finger millet actually grows in drought conditions. You don't even have to grow it. Like, it's a grass that grows automatically with very less inputs. And from a physical standpoint, it's the functional properties of this millet is also great, like the viscosity, the way it, like the iron content, the calcium content is amazing. So when a country has iron deficiency anemia, if we could incorporate this millets into their diet, that would be a wonderful thing. So currently there is a trial that's happening in parts of India where they are substituting with iron-enriched, iron biofortified pearl millet and finger millet, and in midday meal school systems, like school meals, to see if there is an increase in the iron content in children who are consuming it. So there is a lot of potential for that. And also it tastes yummy. Like, if I consume it, so it tastes yummy and it's good. So it's like quinoa. The size is like quinoa, but it's brown. It's chocolatey. If you have a powder, it's like more chocolate color.
I have a follow-up question on that. On the amaranthus. I grew up in a farm, and amaranthus, there is a lot of different species, but there is some of them that they grow. It's a nightmare. They grow everywhere. It's very difficult to get rid of them. Now, the one that you were showing, it's for human consumption. I'm wondering, is the one that for human consumption easy to grow? Do they germinate easy? Because I'm doing some experiment on food waste transformation and composting, and they said actually amaranthus is one of the best species to test phytotoxicity of compost material, because it's very sensitive. So, and I saw it with my test, it doesn't germinate if there is too much compost and so on. So which one it is? Are they easy? Are they drought tolerant? The one that you showed?
So the one that we're using is a drought tolerant variety, and it's like golden crimson gold. That's the variety that we're using. And Dr. Rob Myers from the University of Missouri, he's the director for regenerative agriculture. So he's a plant breeder, and that's where he grows that and he gives us, and we do the processing. So I'll be happy to introduce, or because he has got germplasm and all those information.
Yeah, I was just curious to know which variety it was, and if it was easy to grow for human consumption or not.
The thing is crimson red. That's the one that
yeah.
we show.
Okay, thank you. Okay, I think. Let me see. No other question.
We're right at 11:50, so maybe it's the perfect timing to wrap up, I guess. Well, thank you so much for a wonderful talk and a wonderful Q&A session as well. Lots to chew on, if you don't mind my pun.
Thank you all for very thoughtful questions. Like, it was really nice to talk about this.
Yeah, thank you so much for the talk and for giving the talk from India at 1 a.m. in the morning. Thank you.
Thank you. Bye-bye.
Bye.